Hello everyone, today we will learn about the Boolean algebra and their laws and rules. Now let's begin the video. So laws of Boolean algebra. Boolean algebra uses a set of laws and rules to define the operation of a logic circuit, as well as the logic symbols 0 and 1 being used to represent a digital input or output. We can also use them as a constants for permanently open or closed circuit or contact respectively. A set of rules of or law of Boolean algebra expression have been invented to help reduce the number of logic gates needed to perform a particular logic operation, resulting in a list of functions theorem known as commonly as the laws of Boolean algebra. Boolean algebra is a mathematics we can use as analyze digital gates and circuits. We can use the laws of Boolean to both reduce and simplify a complex Boolean expression in an attempt to reduce the number of logic gates required. Boolean algebra is therefore a system of mathematics based on a logic that has its own sets of rules or a law which are used to define a reduced Boolean expression. So here we have a chart that represents the Boolean expression, description, equivalence switching circuit and Boolean algebra law rule. Now A we can consider A is an input and Boolean expression 1. So A can be anything, 0 or 1. So 1 plus 1 or 1 plus 0 is equal to 0. We all know that. A parallel in with closed circuit we call it. Equivalence switch circuit, here we have a closed circuit and an open circuit, and it is all annulment. So in second one we have A plus 0 equal to what? A is parallel with open A. So here we have an open circuit and its gates also open, so it's identity. Okay, so A into 1 or A dot 1, we can say that A dot 1 equal to A. A is a series with closed A. So A here we here have a switch and it's a closed circuit, so it's also an identity. So A dot 0 equal to 0. A in series with open equal to open. It's a completely open circuit, so it's annulment. Okay, A plus A in parallel with A equal to A. So here we have two gates which are parallel to each other. Now in second one, A dot A equal to A series with A equal to A. Okay, here these gates are connected in a series. So A equal to A, its input and giving the output, and the second one is giving having the output as an input, then it's giving the output. Not A equal to A, not A, not A. Here we have a not A, or we can say that A bar. So it's saying that it has double A bar. So not A, double negative equal to A. This can be defined because it's equal to A, it's only a gate. So A plus A bar equal to 1. A in parallel with not A equal to closed. Here it is a closed, it's complement. Okay, A dot A bar equal to 0. A in series with not A equal to open. You see, it is not in series, so it's a open and it's also a complement. Okay, and again we know this A plus B equal to B plus A in parallel with B in parallel with A. We can reverse this as a here we can have B and here we can have A, so it's remain the same. Or A dot B equal to B dot A in series with B equal to B in series with A. Okay, now let's move on to the next, that invert and replace or with and. So we have OR gate which we are replacing with AND. Okay, or a plus b whole bar. We are replacing a bar and b bar. Here we invert and replace a and with or. Here we are replacing AND gate with OR gate. So a dot b whole bar equal to a bar plus b bar. These both sequences are used in De Morgan's theorem. We will learn about the De Morgan's in upcoming sessions. Now let's look at the basic laws of Boolean algebra that are related to commutative law, allowing a chance in position for addition and multiplication, a assertive law allowing to the removal of back brackets for addition and multiplication, as well as the destructive law allowing the factoring of an expression are the same as in ordinary algebra. Each of the Boolean laws above are given with just a single or two variables, but the numbers of variables defined by a single law is not limited to this, as there can be an infinite number of variables as input to the expression. The Boolean laws details above can be used to prove any given Boolean expression as well as the simplifying complicated digital circuits. A brief description of the various laws of Boolean are given below with a representing a variable input. So description of laws of Boolean algebra. So let's start with Enrollment Law. A term and ed with a 0 equals 0 or odd with a 1 will equal. So a and 0 equal to 0. A variable and with 0 is always equal to 0. It's a law, and you have to remember this because it's a very important basic concept of Boolean algebra. We have a or 1 equal to 1. A variable odd with 1 is always equals to 1. Identity law. A term odd with a 0 or and with a 1 will always equal that term. A or 0 equal to a. A variable odd with 0 is always equal to the variable. A and with 1 equal to a. A variable and with 1 is always equal to the variable. Now an input that's and or odd with itself is equal to that input. Okay. Now a and a equal to a. Oh, how can we say the a and a equal to a? We can say that a and a plus a equal to 2. But here in Boolean algebra we have only two variables, 1 and 0. We always work with two variables, 1 and 0. So besides that we don't have any other variable. So always two input which can be 1 equal to 1, 1 plus 0 equal to 1, 0 plus 0 equal to 0. It's a basic concept. You have to remember that. A odd a and a equal to a. A variable and with itself is always equal to the variable. Now complement law. A term and with the complement equals 0 and the term or with complement is equal to 1. A and a equal to 0. A variable and with its complement is always equal to 0. A odd a equal to 1. A variable odd with its complement is always equal to 1. Commutative law. The order of application of two separate terms is not important. A or a and b equal to a b and a. I am saying dot as an and, okay, because it's AND gate. It represents AND gate, as well as plus in represent the OR gate. Okay. Now the order is which variable are and makes no difference. Order which variables are odds makes no difference, because I can write a plus b equal to b plus a. It's both are correct, so there is no difference between A plus B or B plus A. Okay. Now double negotiation law, a term which inverts twice is equals original term. Okay, here we have A dot A or double A equal to A. A double complement of a variable is always equals to the variable. It's also a term, you have to remember that. Now let's move on to the De Morgan's theorem. De Morgan's theorems are two. There are two De Morgan's rules of theorem. First one is two separate terms not together is same as two terms inverted or complement, and for example A or B equal to A and B. Okay, now two separate terms and together is the same as the two terms inverted by complement, or for example A dot B equal to A plus B. Okay, Boolean algebra function using information above. Simple two inputs and or not gate can be represented by 16 possible functions as shows the following table. Okay, I made this table for you guys so you can understand it better. The function, description and expression. What the number one function we are studying is a null function. Null represents 0. It's the expression. We write this expression and we know this expression as null function. Okay, now second function is identity 1. We identify 1 as an identity. Okay, third function is input A. A is an input, same as for B. Input B is an input. We B remember as an input. 5. Not A. Not A or bar A. A bar we can call that. Okay. 6. Not B. Not A or bar B we can call that. 7. A and B. A and B we can write it A dot B. Okay. 8. A and not B. A dot not means bar. A dot bar B, it is equal to A and not B. 9. Not A and B. Not A means A bar. Not A means A bar and dot means and B. So we can say that not A dot B. Okay. Not A and Nand. Sorry. Not A Nand. So what is not A? Not A is here and Nand is a total bar. Dot plus totals bar. Okay. 11. A or B. A or B means A plus B. 12. A or not B. A or means plus or not means B bar. 13. Not A or B. Not A means A bar plus B. Not or not. And exclusive or means we can say that as a XOR XOR, we call it XOR or exclusive NOR. So if what is exclusive NOR? Exclusive NOR is a complex Boolean expression we express as opposites of two inputs opposites like two inputs bar and their summation, like A dot A and bar not B or not A and B. Or exclusive NOR is the opposites, that A and B or not A and not B. Okay, so this was the brief explanation about the laws of Boolean algebra. If you have any queries, please comment down the video, and now we will learn about the type of basic logic gates. Okay, so in this part we will learn about a different thing, which is type of basic logic gate. So there are several basic logic gates used in performing operation in digital system. The common ones are OR gate, AND gate, NOR gate, SOR gate or XOR gate. Additionally, these gates can also be found in combination of 1 or 2. Therefore, we get other gates such as Nand Gate, NOT gate, or exclusive OR gate, or XOR gate, or exclusive XOR NOT gate, etc. OR gate. In OR gate, the output of an OR gate attains the state 1 if the one or more inputs attains in the state 1. So the expression OR gate is y equal to a plus b. We express the OR gate as a plus sign that reads y is equals to a or b. So here is the truth table. From the truth table we can see that a has the input of 0 0 and 1 1, b has the input of 0 1 0 1, and the a and b equal to y. So 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, and 1 and plus 1 equal to 1. We have seen this type of mathematical equation in the previous part. AND gate. In the AND gate, output of an AND gate attains the state of 1 if all the inputs are in state of 1. Or if all the inputs like a equal to 1, b equal to 1, so the output will remain 1. The Boolean expression of AND gate is y equal to a dot b, or a. The truth table of the two input a and basic gate is given as a 0 0 1 1, b 0 1 0 1 0. Okay, so a dot 0 dot 0 equal to 0, 0 dot 1 equal to 0, 1 dot 0 equal to 0, and 1 dot 1 equal to 1 from here. Okay, and this is the picture of an AND gate. AND gate should be look like this, like it's a half round circle and this is a spherical. Okay, now NOT gate. NOT gate, the output of a NOT gate attains the state of 1 if only if the input does not attain the state of 1. So in NOT gate the input should be complement, as I have told. If the input is a, then the output should be a bar. The Boolean expression y equal to a is here, the a should be here. Okay, reads y equals a. The truth table of NOT gate is follows as a y equals 0 1 1 0. NAND gate, the basic logic gate of combination of AND and NOT gate equal to a input b input equal to AND and NOT gate. So NAND gate is the basic combination of AND or NOT gate. So here we have AND gate, and here and we have the NOT of NOT gate. Okay, the Boolean expression NAND gate is y equal to a bar dot b. Okay, the truth table of NAND gate is as the input are a 0 0 1 1 and b 0 1 0 1. So the output should be 1 1 1 0. Okay, NOT gate. The gate is combination of or NOT gate. So here we have a OR gate and a NOT gate. So the Boolean expression NOT gate is y and a is whole. It should be whole bar. Okay, a plus b. The truth of the NOT gate follows the truth table of the NOT gate follows this, as inputs is 0 1 0 0 1 1 0 1 0 1. So the output should be 1 0 0 0 0. Okay, the exclusive OR gate, but XOR gate, we call it XOR gate. In XOR gate, the output of two inputs XOR gate attains the state of 1 if adds only input attains the state 1. A and B, those are the input, and here we have the XOR or exclusive OR gate. It's a normal OR gate, and here we have a line which is not straight, curved line. So it is the total picture of XOR gate. The Boolean expression of XOR gate is a dot b bar plus a bar dot b. So or y equal to a XOR y. We call this sign as a XOR sign, that is XOR. Okay, the truth table of XOR gate is a as the inputs we know, a 0 0 1 1, b 0 1 0 1. So the output should be 0 1 1 0. Okay, exclusive NOR gate. Now let's move on to the exclusive NOR gate. Okay, or in XNOR gate, the output in the state 1, which is both input are the same, that is both 0 and both 1. So in exclusive NOR gate, it is the same picture as this is, but here's a little difference. We don't have a NOT here, but we have a NOT here. So what is exclusive NOR gate or exclusive NOR gate? It is the complement of exclusive OR gate by XOR gate. Is the complement of XOR gate. We call it exclusive NOR gate. Okay. Here we can see it is the XOR expression, XOR gates expression, and we have a complement or bar above that. So it's an exclusive XOR gate. It's the same concept that it's no only the complement of XOR gate. Okay. So here we have 0 1 1 1. So if we make the its complement, so it should be 1 0 0 1. So let's see in the XNOR gate 1 0 0 1. So it's the simple complement of XOR gate. So these are the some simple gates, and it is we have to always we should always be aware of the symbols, because these are the most important which comes in the exam. This is NOT gate, this is AND gate, this is OR gate, and these symbols are the basic gates of the logic gates. And above all that, what are the universal gate? A universal gate is a logic gate that implements a Boolean function without having the usage of another logic gate. The universal gates are the NOR and NAND gates. So we call NOR and NAND gate as the universal gate. So thank you everyone watching this video. Please like, share and subscribe. Till then, bye.